Hello and welcome to End-to-End Stack presentation. We are going to talk about YugabyteDB and its ecosystem solutions to build globally scalable applications. My name is Yogi Rampuria. I'm a principal solutions engineer at Yugabyte. I'm based in Singapore and I look after the channels and alliance partners in Asia, South and India. I'm a very enthusiastic open source supporter. I have been using, contributing, buying, and selling open source solutions for quite a while now. In recent times, I have been working more on the Kubernetes and cloud native ecosystem. I do have my roots in application development, primarily with Java, but also with other programming languages. I am extremely big proponent of developer experience. So everything that I do, I try and actually look for developer productivity aspects in it. So why are we here? Why are we talking about end-to-end stack? Let's take a step back and try and see what are the current trends that we have seen in recent years, last couple of years, I would say. Cloud native applications are on the rise. Everybody have sort of accepted cloud native applications as the de facto standard for building out anything new, any new experience that you are building. You have to be using cloud native applications or cloud native architectures to implement it. Cloud adoption, public cloud adoption is actually also on the rise. We are using more and more cloud provided or cloud accelerated experiences. It could be SaaS-based applications, or it could be more of a PaaS or a platform as a service kind of solutions, or just about anything in between, really. Something new that is sort of emerging in last couple of years is the increased attention to multi-cloud and multi-region architectures. Primarily, businesses are looking to expand to more and more geographies. So they want to actually build application that can match their customers' experience based on their geographic profile. So multi-region and multi-cloud solutions are something that people are starting to look more and more eagerly. Now, when you put it all together, cloud native applications, containers, Kubernetes, and multi-cloud, well, it blows your mind because yes, it can be really complex. You end up with questions like, will it work? I'm going to use this particular technology. Will it work for me? Or you have existing solutions and you want to make them work with, say, cloud native applications or Kubernetes in multiple cloud environments. Are they going to work together? And when it doesn't work, it can be frustrating, but not as frustrating as how is it working? Why is it working? And I have had that issue many a times in my career. So let us just go back to the beginning and try and understand why are we here, how we are doing this. So in the beginning, about 14 billion years ago, no, I'm not going to go back there. Let me stop. I'm just kidding. I'm going to start really where it matters, an app. Now, what is an app? Is it an app running on your phone? Is it a software? Is it a piece of code or anything in between? In this context, we are going to say it's a piece of code that is running somewhere. And that's going to be my assistants along with a few others. So you will see them all over my presentation. So an app is something that would typically run on top of a virtual machine or a pod. Pod is the smallest unit of compute in Kubernetes. Now, along with your application, you generally have these supporting systems. It could be an agent, a sidecar, some other container, which is sort of providing a cross-cutting capability. Log aggregation, security agent, enforcement of compliance policies, or just general monitoring, so on and so forth. Right? So all these things, they make up your instance of an application. And typically, it's never alone. You always have multiple of these for high availability. And all these instances, they run on top of a runtime. It could be a Kubernetes-based runtime. It could be a hardware-based runtime, a hypervisor, or some sort of a bare metal server or something. For our discussion today, we are going to look more at Kubernetes. And why is that? You'll find out in a minute. But before we go to that, let us just also acknowledge that your application is actually sitting with certain services which are providing you with the capabilities that are needed from a data persistence perspective. So for example, you want to have database, you want to have event streaming services like Kafka, you want to have identity and access management, maybe Vault, and things like those. So all these things, they are also important part of your application ecosystem, and they need the same level of details in terms of resiliency, uptime, as your code. So whatever we discuss and decide to do with our application, same aspects, NFRs, are also applicable for these services. Now, in this architecture, you can kind of see that we are thinking of services on top of Kubernetes. And especially if you talk about database on top of Kubernetes, that is not something that everybody is very comfortable with. And rightly so. There are reasons for doing it and there are reasons for not doing it. Let us just examine those and let's take a slight detour. But before we go there, remember, all these things that we have discussed so far, it could be multi-site. And when I say a site, it could be a site, it could be a cloud region, or an entire different cloud, right? And whatever complexities that you have thought of so far, well, you can double and triple it. Yeah. So let's take a slight detour and I examine just the services part of it on Kubernetes. So especially databases. Why would you run databases on Kubernetes? Well, to begin with, it actually optimizes your resource utilization. It can reduce your cost by better packing all sorts of processes into lesser and lesser hardware footprint, or say virtual machine footprint. So this actually makes it extremely viable for large implementations. You can actually run large number of servers with like a multi-tenanted kind of an approach. You can have your self-service private DBaaS kind of solutions, which can actually help you in optimizing your spend and making your operation far more efficient. But obviously, it comes with a set of problems, very specifically a noisy neighbor problem. So you can have performance issues creeping up because of multiple database nodes sitting on the same sort of virtual machine or something like that. Some of these things can actually be avoided through the constructs in Kubernetes. And we'll talk about it through the subsequent slides and demo. The other part is the ability to dynamically change your resource allocation. So in Kubernetes, very specifically, you can have horizontal scaling. That means you can actually add more and more instances of your component, a database, or you can make the components bigger. So horizontal pod autoscalers and vertical pod autoscalers are something that can actually help you in increasing your resource allocations dynamically. It also provides you with an ability to make your application much more portable. Kubernetes is more or less an acceptable API for infrastructure automation today. And your experience is almost same across the cloud providers, be it like AKS, EKS, or GKE, or like TKE on Tencent or Ali Cloud Kubernetes. All those things, pretty much the core of it is exactly the same. So you're able to portably run your applications, the database, on these cloud providers. They also provide you with self-managed Kubernetes on public and private clouds. This is the likes of OpenShift or VMware Tanzu or Robin, Rancher, all those. But having said that, no two Kubernetes are exactly same. There are differences in terms of storage classes and load balancers, and especially coming from an application background, it can be really daunting to understand these nitty-gritties and implement it. Now, also Kubernetes provides you with an infrastructure orchestration. As I mentioned earlier, Kubernetes is sort of accepted as an API for infrastructure. So if and when a pod fails, it is restarted automatically. It's resizing, its placement across the nodes. Everything is sort of taken care absolutely dynamically. But this also makes a bit of a challenge for a traditional sort of a deployment approach, because nothing seems to be permanent. The IP of the pod may change. So how do you have a resilient way of actually reaching the pod all the time? Well, there are solutions around it, and we will discuss about those. The day two operations can also be automated in Kubernetes. So typical things like backups of databases and database upgrades and things like those, they can actually be very easily done through Kubernetes custom resource definition capability. And we do use those. The challenge is, if you are using a traditional RDBMS, these things can either cause data loss or service unavailability. So in order to mitigate absolutely these two issues, you are better off actually using a distributed SQL, a distributed database. Why would you not run database on Kubernetes? Well, remember this, pods are ephemeral by nature, so they tend to get restarted or fail more than a virtual machine or a bare metal host. Their IPs would change. So if you don't have a reliable way of reaching these pods, you're going to have problems, right? The failure rate can actually be high because sometimes you may over provision certain servers. So you may have out of memory issues and some of the operators on the Kubernetes kicking in and killing off pods if they are overutilizing the server. And the rescheduling of these pods is fairly transparent. I mean, a pod can go off from server number 1 and it can come up on server number 3, and you wouldn't know about it. So you need a reliable way of reaching it in order to mitigate this. Using a distributed database is actually a very good solution for it, because these disruptions, these failures, they actually cause disruption of the service or data loss. This one is also quite important. When you actually run a service, whether it is database or any other service, when you want to access it from outside of Kubernetes, it could be difficult, especially if you are in a private environment, a private cloud environment, because load balancer is not something that is available readily there. You may have actually hardware-based load balancer, or maybe the load balancer does not have an API-driven approach of reconfiguring. So on public cloud, it's relatively easy, but you still are confined by the quota limits and all those things. So you have to be aware about those things. But on private cloud, definitely reconfiguring of the load balancer is a challenge. And the networking complexity that comes with Kubernetes, because here you're talking about 3 layers of networking, right? So you have your worker node networking, you have your service sort of a network, and then you have your pod level network. The pods are actually not visible. The pod network is not exposed outside. So you have to rely on DNS-based capabilities of the Kubernetes to be able to reach the pods of your stateful workload vis-a-vis database. Now, you can also leverage things like a service mesh or Istio, but that may lead to lowered performance. So again, when you're looking at multiple Kubernetes clusters, the network and service discovery can actually be challenging. So this is another reason why you wouldn't actually run a database on Kubernetes. But if you want to run a database on Kubernetes, it has to be a distributed SQL, because all these do's and don'ts that I spoke about are actually being addressed by that. So you have the same benefits that we spoke about, right? Resource utilization, resizing, portability, and infrastructure orchestration and automation of day 2 work. Plus the key issues, that is the failure, the greater chance of failure. How do you mitigate it? Distributed SQL actually mitigates it. The local storage versus persistent store, that is also addressed by the distributed SQL database. And the load balancer and the networking complexity and the operational maturity is also addressed by YugabyteDB as a distributed SQL through its use of a variety of Kubernetes artifacts. This is a typical deployment of YugabyteDB on Kubernetes. So essentially, you have 2 stateful sets. which one is for the master and the other one is for the T service. And the master service is exposed outside the cluster or within the cluster through a headless service. The T service pods are also exposed through a headless service. And you see the application clients accessing the T server for the YSQL and the YCQL APIs via the headless service. Now, going back to our application and the common architecture, right? Now, this is something that we are very, very familiar with, right? You typically have two sites, production and DR. It's not active-active. It's an active-passive kind of a setup. All users, they typically go to one site, and all the applications and services that are running on that site, they sort of come together to provide all sorts of orchestration, right? Now, in case of a disaster, you move all the services here. You basically bring up the services, the application, and reconfigure the network to start sending users to the other side. So in an active-active scenario, broadly, you start out with this kind of an architecture where you have multiple sites and you have these layers of infrastructure, and each one is sort of taking care of its replication or state translation or transfer. And then also along with the cloud native architecture evolving, the personas are also evolving. At the beginning of, say, 2010s, we had application developers and engineers. But today, we see more and more sort of segregation in terms of the duty. You have like application engineers or DevOps engineers, which are actually responsible for everything pertaining to an application. They are also responsible for consuming the infrastructure APIs that infra engineers actually put out. So infra engineers would use tools like Terraform or Pulumi, things like those, to actually provision, monitor, and manage the entire infrastructure. The application engineers, they would typically build and deploy and configure the applications through the likes of Jenkins or GitLab, and they would use things like container registries to push their code, and also deploy the applications through the use of containers and deployment files. The database reliability engineers are people who actually, especially when you start using globally scalable databases, they are the ones who can actually advise correctly on the level of partitioning details and all those things. So these personas are also evolving. Though all those personas are different, but all of them tend to have a similar goal. They want to automate everything, well, almost everything, right? So how do they do these things? Typically, you would have a CI/CD or a DevOps sort of pipeline that would take care of taking a piece of code and putting it to the other side. Now, in case of an application, you would have a source code getting packaged into a container, going into a runtime state of an app. The data engineers would typically use the SQL or the APIs or CLIs to provision and manage these services. The infrastructure engineers, they would use the infrastructure as code tools or cloud APIs to provision the infrastructure to support this whole thing. So that brings us very nicely to the first demo. Here is an application that it's a Spring Boot application with a React front end. Everything is packaged as one. And this application is generated through the standard start.spring.io page. And what I have done in this is I have added a couple of extra things over and above what the start wizard actually adds. So first thing that I have added is I have added the Yugabyte YSQL dependency, the starter dependency, then for the Spring data. And then I have added the database driver for YugabyteDB. And I have also added over and above that, I have added a test container for YugabyteDB. So this actually gives us the ability to test the application end-to-end, front-end, back-end, and database, everything together. So the application itself is pretty straightforward. You have, this is the main class of the application. This is the test for it. And I mentioned the test container. This is how the test container is actually being used here. So we actually pull the latest YugabyteDB container. and give it a create a database name, add the user and a password, and then use those things to actually run the database for our test cases. Also, there's a small web configuration here that actually allows the React application to work smoothly with a Spring Boot application embedded in it, and you don't need to actually package it separately. This is a simple service, a greeting service that I have implemented just to test that everything is working properly. So let us actually go ahead and start this one. So what I'm going to do is I'm going to run the start of the NPM, and I'm also going to run the backend Spring Boot application. What I have also done is I have gone ahead and started a database server here locally which is a YugabyteDB server. And currently it doesn't have the tables or anything that I would require for my application. Just as is now, I'm going to actually open this in my browser, and this is the application. So we just run the schema SQL file against the database. Now, if you want to check out what exactly that looks like, it's a very simple SQL file that has a simple order table and a data file that has 5 records in it. And now, if I run this application again, the way it will work is it will actually have, I need to check out the next version of the application where I have the backend for this configured. So the REST API for database. So if I examine it here, this particular number 4 is where I have created an order repository, an order class, and the orders front end component is updated, and so on and so forth. So each one version of this application is actually tagged in the repository. You can actually check it out yourself as well later. So going back, if I go ahead and start my application and my front end and the back end, now all this data is actually coming from the back end. So if I refresh this, I can now insert an order. So if I say Yogi and Singapore and Amex 1234 2212, and then I say save, and you have the order that was actually executed. And if I go and try to see the data in the database, you can see the data is actually present in the database. The end-to-end database testing. So let me try and do this. So here's a piece of code where I'm going to test the database connectivity. So if I go and just run this particular test case, now what this will do is this is where the whole ecosystem part comes into play. Test containers is a very well accepted framework for building applications and test containers, using test containers to simulate the supporting services. We are using the same test container setup here. And over here, what I'm doing is I'm actually bringing up a Docker-based container for YugabyteDB and running a query against it. Going back to this, as you saw that we've built a very simple application that can actually run end-to-end on my machine. I can use Docker also for it. The repository actually has instructions for using Docker also. But what about actually running it on a global scale in multiple Kubernetes environment? Well, first off, let's say instead of doing 2 sites, let's do 3 sites just for fun, right? And the way we think about it is we actually are going to have separate Kubernetes clusters, which are in different regions, one in US, one in Europe, one in Asia. And then we are using Google Cloud right now. And we have the GKE, 3 different clusters. And YugabyteDB is something that is actually replicated, a globally replicated instance of YugabyteDB. And the applications are independent instances. And you have ingresses, which are actually providing it with the connectivity. So now the provisioning of GKE and all the cloud infrastructure it can be a little elaborate, and it can take like maybe a couple of hours to finish. So I have gone ahead and done all that. And you can actually find all the scripts and all the nitty-gritties about it here. Check out. So all the artifacts and documentation is actually present here. Now, for every deployment on cloud, I have created a separate folder. And for every Kubernetes, I have created the environment specific YAML files for it. Now, you can actually use different tools. You can use Helm, you can use YTT or customize, variety of tools to actually achieve the same result. I have gone for a very simple approach whereby I create all the artifacts, environment specific artifacts, and put them in the repository there itself. Now, what I did was in the beginning, I created the Yugabyte deployment and stored everything in this YAML file and deployed this YAML file. As a result of that, I have YugabyteDB running in US, Europe, and Asia. And all these things are actually accessible. They're replicated instance of each other. So if I look at the service here, and this is the master UI, if I go here and open this UI, it shows you YugabyteDB universe with replication factor of 3 and 3 T servers associated with it. If I go to tablet server, I can see the cluster set up here and also all the tablet servers and everything connected to it. Now, with that in mind, what I'm going to go ahead and do is simply build the whole application into a Docker container. And as part of the container build, what it also does is it compiles the React application and packages it into the Spring Boot application. So everything becomes like a single package. If you want to run it locally as a jar file, you can do that. If you want to run it in a container, in a Docker, you can do that as well. Or you can use the same Docker image and run it as a cloud-based application or a Kubernetes-based pod application. So internally, the Spring Boot actually uses the build pack. So this is the image that was built by this, and I am going to just Docker push this image and deploy, send this to the registry. Now, what I have done is, as I mentioned earlier, I'm going to deploy this application independently on every cluster. So this is my deployment for Asia Pac, where I have, I'm using the same image that I built just now. And I have made sure that I assign it with the proper resources. I have also provided it with the deployment strategy so that later when I update these applications, they are done easily. And I'm exposing the pods, and the actuator that I had actually discussed earlier is being used here. And then all these things and this particular configuration is being used to feed the environment specific configuration to this application. And the application is exposed internally as a service and then externally through this ingress. And this is the URL which the application will get deployed on. Currently, if I go and see, there is nothing actually. If I refresh this page, nothing. So all three of them are not working right now because I haven't deployed it. I'm going to go ahead and actually deploy the application now. What this will do is it will go and deploy my application on each of those clusters. And in each of those clusters, the application is set up to connect to a YugabyteDB instance locally. So now the application is actually deployed, and I'm looking at the ingress controller, and I can see the address and the IP. Now, if I go to the browser and go to this URL for each one, you can actually see the application getting sourced from each of the regions. So this is US, so this is coming from US, this is EU, this is coming from EU. And for each one of those applications, they are connecting to their local instance of YugabyteDB. And same thing for Asia Pac. So this is connecting to the Asia Pac cluster locally. And then if I go ahead and actually make a insert order, so let's see, Yogi, Singapore, 1234, 123, 12. Don't use my card, save. And you can see the order was inserted successfully. If I go here and refresh it, I should actually, yeah, there you see my order. Yeah, and I can see it here. So you just saw me actually place the order on the US instance, and the data actually got replicated everywhere. So this way, we have actually built an application that is scalable globally. We are able to deploy the application on each of the individual Google Kubernetes Engine cluster, and we are able to have a database that is replicating the data all over. So this makes your application development extremely easy, but the data service is actually globally replicated. This is actually the architecture. I have used GKE for this particular connectivity. You could leverage something like Submariner or any service mesh for it. But for this case, I have used the multi-cluster service from Google Kubernetes Engine. We've already been through this. So with that, thank you very much. Thanks for joining today. Please reach out to us on the community Slack. Thank you.